Hi everybody, thanks for your time. Welcome to High Performance Computing and AI, Artificial Intelligence for Everybody on Microsoft Azure. My name is Carl Podesta. I'm a HPC technical specialist for Azure, working in the EMEA region, so Europe, Middle East and Africa, and I work every day with customers, engineers, scientists, researchers doing high performance computing on Azure. And I'm here today to give you a little bit of a view into that and how SUSE is a great partner for us and how we have great capability to work together and push forward science, engineering, research using Microsoft Azure, high performance computing and AI. So let's move to the presentation. To tell you a brief bit about me, I'm Irish and I'm based in Dublin. So I'm also a little disappointed I won't welcome all of you and meet you in person here for SUSECON in Dublin this year, 2020. But maybe another time, and it's not just for that reason, but it's actually because I have a history here in Ireland. My career started as a SUSE engineer, and I worked for a number of years here as a consultant in Ireland, running Linux and high performance computing systems. And for a while, I was one of the only certified SUSE trainers in the country. So anybody who obtained a certified Linux engineer or professional certification probably did courses with me and exams with us. A shout out to my ex-colleagues at SecureLinks, who are a very well-known Irish SUSE partner. So now today, let's go straight into it and tell you why HPC is so important to us day to day, how the cloud is going to make this more accessible, more available, more extensible for everybody, and why you might want to do that also with Microsoft Azure. So let's keep it fairly straightforward. We have about 30 minutes, so I've separated it into two sections. The first bit is we'll talk about high performance computing generally. We'll talk about why the cloud makes that, again, like I said, more extensive, more accessible to so many people. Why would you choose to do that with Microsoft Azure and with SUSE? And tell you a little bit about what's happening in terms of an industry context, customers and partner ecosystem that has been developed over the last number of years with HPC on Azure. In the second half of the presentation, how could you do it? So how do we actually set it up in terms of the architectures, the orchestration tools, the components such as compute, storage and networking, and where can you go to get more information? So why HPC and why HPC on Azure? HPC stands for high performance computing, and some people know it as supercomputing. So this is something that actually affects every one of us every day. So the cars that we drive have typically been designed for safety on a supercomputer or a high performance computer. The houses we're in have been designed also in terms of a computer aided design or architecture diagram. The entertainment we watch on television, videos and media entertainment has been typically rendered with high performance computing. The weather every day gets predicted on supercomputers around the world. So what will it be like today, tomorrow, and in days to come, and in terms of our weather climate? And actually then curing disease and finding disease. And even in our current situation with COVID, a lot of work is ongoing on supercomputers and HPC systems around the world, including on Microsoft Azure, to try to find out how we can fight COVID-19 as things are happening right now. So day to day, all of us are affected by a large simulation, a large calculation that has either been done in the past or is currently being done, and these run on high performance computers. And basically, these are computers combined together to do a particular task. And some of the pictures on the screen illustrate this. So very typically in some industries, like in financial services, for risk calculations, finding out what will happen in the global markets if you make certain decisions or stock trades. Searching for energy, so oil and gas and beyond, how can we find the right place to find the energy, pull it out and use it? How can we, again, design safer cars? All of these things rely on high performance computing. In Microsoft, our mission is to enable every person and organization on the planet to achieve more, and this is reason enough for us also to be involved in high performance computing. So over the last number of years, Microsoft has built a large team globally spanning multiple different parts of the organization, all working together to enable scientists, engineers, researchers, anybody who's utilizing high performance computing to get faster simulations, cheaper simulations, to do more simulations, to also help think outside of the box. So normally we might have been restricted to high-end supercomputers to do our work, but what happens when you put the power of the cloud in the hands of anybody to be able to do a simulation? You can simply spin up a large number of machines to do a calculation for a few hours, a few days, spin it down when you don't need it. You'll pay for what you use, and then you get an answer that you can use. And if you had that power available to you every day, what would you do differently as a scientist, as an engineer, as a researcher? So this is also what's exciting to us in Microsoft at the cloud vendor side of things. How can we enable researchers to do more with this and to think differently about it using the cloud? And some of the reasons that people are choosing to use cloud for HPC are outlined here. So it's not just the scale of multiple data centers and machines across multiple locations to do even a single simulation or multiple simulations, but it's that elasticity to make it larger, to make it smaller, to only pay for what's eventually used. And then like that, to bring it to different parts of the world. So other colleagues, scientists, researchers working in different parts of the globe can also access the same computing power with ease, same data with ease, and also to choose multiple different types of compute for what you need to do. So maybe you need a GPU, a graphical processing unit. Maybe you need a CPU, or you need some disk, or whatever configuration it is that you need typically will be available to you in the cloud at various different levels. Again, a lot of our customers are interested in doing the science and engineering part of things, but sometimes they have to maintain a supercomputer infrastructure, data centers, to be able to do that. And that's not always what they want to do. That's not part of their direct business. So with the cloud, you don't have to own that infrastructure. You get a known cost for a single simulation. And this is a really powerful thing in terms of management, in terms of the hassle of maintaining this infrastructure, but also in terms of the business, knowing to go to the business to say, well, if we were to do these number of simulations additional, this is how much it will cost us, and this is how much it would mean to our business and our research. So this is also an important topic in HPC, where we also want to prove the value of what we're doing. So this is a great reason also to use cloud, to make some of this more transparent and clearer to the business as well. In terms of why you might use Microsoft Azure for that as well, I mean, we have a number of features and the like that I'll bring you through shortly, but I mean, there's a number of pillars also that we're built upon. In terms of the capacity being on demand, so when you want it, you really can run large-scale parallel and batch compute jobs in the cloud. But it's also extensible, so you've already made investments in a HPC cluster on your site or some workstations, and you want to just burst out to the cloud when you need it. You want to extend that and leverage your existing investments and any new burst capacity in the cloud. And you might want to do that in different locations. So you really have that sort of flexibility and extensibility with the cloud. And one of the final pillars is scalability. So I mean, the fact that you can actually scale up and down easily, accessing these real HPC capabilities and features is again something that normal people operating supercomputers and clusters today on premise have a difficulty to do. And for Azure in particular, we have a number of differentiators, a number of things that set us apart from the others, and that's in particular the ability to do real HPC. So tightly coupled simulations which rely on a very fast network to be able to send messages between them. So on multiple machines, hundreds of machines, you can imagine, different processes all working together on a particular problem. They'll also need to talk to each other, coordinate together, and typically that's when they rely on a network like InfiniBand, like RDMA, remote direct memory access, in order to be able to pass these messages very quickly to each other during the simulation and get it done very quick. Azure has InfiniBand baked into it in a number of different locations, accessible to many of the HPC components that we'll soon see. We also have a broad partner ecosystem. We work with not just partners developing software, but partners implementing HPC solutions for customers. Science and engineering software tools themselves. We're working on all parts of the partner ecosystem to enable scientists and engineers to do more. Azure also is differentiated in the fact that we're designing for HPC. So we're not necessarily choosing machines we've already got in our data centers and saying these might be good for HPC. We're actually designing for HPC. And some of our HPC systems are now in their 4th generation over the last few years. We've learned a lot as we're running jobs larger and larger all of the time. And this is getting baked into the systems that we're making available and making available to you. 2 sample benchmarks that have been publicly released recently include a very typical code for computational fluid dynamics, so engineering fluid flow around a car, for example, using ANSYS. So a very popular partner of ours, ANSYS, we've worked with them also to show and demonstrate scaling of their CFD code up to even 12,000, 13,000 cores in a single job, and with relatively high efficiency. So 83% efficiency at 288 of our nodes, 13,000 cores in a single job. So this is the scale that Azure can operate at for some of your HPC workloads. And another popular used code in quantum chemistry, solid state physics, is CP2K. And this is on our Azure HC virtual machines, where we've also demonstrated ability to scale up to more than 22,000 cores in a single job. So you'll find these benchmarks online if you'd like to read more, but it also just demonstrates the scale that currently we're at for some of these applications. I mentioned our broad partner ecosystem, so very happily that includes SUSE at many different levels and engagements with customers, but we want to enable science and engineering like that for as many people as possible. And whatever tools you choose to use and love, open source, non-open source, in different industry domains, not just also in workstations and rendering, but with deep learning and AI and machine learning, which we'll touch on a little later, as well as at the operating system level. What is it that's crucial to be able to allow our customers to do their work most efficiently? SUSE, as we know, has a great legacy in HPC, great power in HPC, and we're very proud to be partners with SUSE in particular to enable more customers to do their work with Azure. So how actually do we do it? Let's talk a little bit about some of the architectures, some of the solutions we've got, some of the components, and talk a little bit more about how we can actually enable HPC on Azure. So we'll start off with a typical life cycle. So this kind of looks like a journey that a lot of customers go through. And it doesn't have to be this way, and customers can also jump into different parts of this life cycle, but it just gives you an idea also about the process. So how do somebody actually start to do HPC in the cloud? And it's not necessarily a big bang situation. A lot of people start small and grow and learn, and also the way they do it can be different in different industries and as suits them, and as suits you. So what is it that's important to you in terms of managing your infrastructure and getting your jobs done faster, jobs done cheaper? So there are a number of workflows here, and this is a typical path that we see a lot of customers going on. So you currently have an application that's on premise, it's on a workstation, it's on a cluster that you already have. And very simply, like a Linux application in SUSE Linux, you could lift and shift that application or clone to cloud in the slide as you're seeing it currently. So no need even to recompile the code. Simply take the executables, move it up to some SUSE Linux machines in Azure, and run the executable as you would normally do with the same version of SUSE on premise. And this is simply called clone to cloud or lift and shift. And it's one of the most basic ways to actually already just get started. You're already leveraging infrastructure, virtual machines in the cloud to run the application normally. And all of the tools that you know and love to continue to do that, to deploy the applications, patch the applications, still apply. And already there's some benefits from doing that. So simply by doing that, you can still have the ability to scale up and down the number of machines for your jobs as you need them. To be able to deploy these in different locations within a few minutes, and really also to give you that scale that we talked about earlier. So already there's lots of benefits for lifting and shifting HPC workloads to the clouds. Customers are experiencing that today. They save money, they provide geographic reach, and they give flexibility. And for many of you maintaining these systems also, there doesn't have to be any change in any of the tools that you're using to be able to do this. What we also see is some customers moving to a more hybrid workflow. So that also includes where we have large data sets on premise. We have instruments on premise, scientific instruments generating a lot of data. These things can't necessarily move to the cloud, or and in order to combine them with the power of the burst, we effectively extend your existing network into the cloud. So like a private bubble into Azure, your machines you'll spin up there could be part of the same network you have and you control securely on premise. And the work will simply go there. So not only just the machines to spin up and do the compute, but what about the storage? So we have ways to sync data across that network to the cloud, data that's only needed at particular times for computing or data that's needed for more. So between the data and the compute, you have this ability to add to your network and develop a hybrid workflow where maybe you have users doing activity on site and then using Azure for simulations. And then we have more maybe entirely cloud workflows. So this includes being able to, for example, create a workstation in Azure, have a GPU card attached to that workstation, and then do a remote desktop where you effectively log on to the workstation in the cloud. You interactively use a high-powered workstation with a GPU to create a model, operate a 3D model, and have an interactive experience, save the work, and then maybe run a simulation. That spins up a cluster in Azure, runs the simulation and executes it. And then when it's finished, you might want to spin up another workstation and analyze the result. And all of that can be completely done in the cloud. And that's what we call maybe an entirely shaped cloud workflow. And then what we also see is that some customers start to use cloud native applications. So these are applications a little unfamiliar to us in the HPC space on premise, but things like functions and databases and caches. Actually, customers can combine these cloud native services together, a bit like a Lego bricks, to get a problem solved. So that also means maybe in financial services where you have information coming from the markets in real time, you want to cache that data very quickly over the internet, and then from that you might want to put it into a database, you might want to spin up some machines and analyze it, and then you want to spin it all down afterwards. And even that's we have examples of an entirely cloud native application to be able to do that. So again, there's a huge capability of infrastructure and services on top of that to be able to leverage what you need to do to get your problem done. And many customers doing HPC problems in different industries leverage these workflows. So let's get back to HPC also a little bit. We'll talk a little bit about some of the orchestration tools and then get into the components. So we have also, I mentioned earlier, a tool called Azure CycleCloud. A nice, very familiar, let's say, for IT administrators, end users, and Linux HPC clusters to point and click and get some icons. You can customize them for a type of cluster that you might want and click and scale it up. It'll integrate with user authentication systems, and really you have power to control this and view and monitor from an IT point of view. Another tool very popular is Azure Batch. So this actually is very suitable for people writing code and developers directly. So you can leverage the Azure Batch APIs in your code to actually spin up the clusters for what you need. So building the power of the flexible HPC cluster facility into your application directly. And many of our partners have already built on top of this service and used Azure Batch to really provide an additional cloud bursting capability into their products. And you'll see that in some of the scientific and end user engineering products also that you see. Also then there's lots of cloud native architectures available. So like that in financial services was the example I gave earlier, but more and more people are now thinking about cloud services, how they can put them together and use them for what they need to do. I won't say finally, because we also have lots of partner solutions that are available on top of all this. So Azure CycleCloud, Azure Batch, there's another one called HPC Pack. These three tools are free for customers to use to be able to spin up clusters of Linux or Windows computers to do these simulations. But also we have many partners who build on top of that. So they put added value around managing workstations, for example, scientific end user software like ANSYS, StarCCM, running on top of Azure natively, and leveraging the power of Azure within the tools to be able to do simulations, and then customers who put some of these solutions together. So we have a wide partner ecosystem. We rely and work heavily with partners together, and maybe there's a particular solution that suits you better as well than managing and creating the systems. And one of the final things to mention that's not on this slide is that as SUSE HPC administrators, you might be watching this presentation, you don't have to go away from tools that you're already familiar with. So to use the native SUSE tools already, the HPC Pack edition, YAST even, and other tools like Ansible, Salt, Puppet, and Chef, from a Linux configuration perspective, can still be used to create, manage these clusters as you see them from the perspective of a Linux IT administrator. So there are so many tools available for you to be able to create and manage this infrastructure available. And we have some guidance about what you might use in different circumstances, but this just gives you a little view. You can already just go to the Azure web portal. So Azure itself can be interacted with from the web portal, from the command line, or directly through code. So on the web portal, you can simply go in and type SUSE HPC. You see a wide number of versions available to you. And for example, that already includes support or don't include support if you have your own subscriptions. So yeah, you can also use these images that are already available to you in Azure, and you can customize your own SUSE images to create clusters really with the configuration that you need. In terms of the compute machines available, there's a wide spectrum of choice. So typically we rely on letters of the alphabet to describe some of these, and actually in HPC we're relying on the H series and the N series. H is the HPC design machines I talked about earlier. We've got HB, really customizing for memory bandwidth, and HC we're typically for dense computing. And the N machines are really GPU and FPGA enabled virtual machines. So to use that workstation I talked about, or to do GPU machines for deep learning or a large calculation, that's with the N series machines. And both of those machines have InfiniBand enabled in them. So to create clusters of those machines with InfiniBand is possible. Finally, for the larger end of the scale, we have a unique capability to provide a Cray directly in Azure data centers. This is in all the regions, US, EMEA, and APAC, and we have a very close relationship with Cray to be able to do this. So if you're running simulations that are larger than 20,000, 30,000 cores and more, and you really need that high scale power at the right price, then Cray is a great option. And we all know as well that Cray operating system has relied on SUSE Linux for a long time as well. Apart from the other virtual machines, it is possible to use them. So again, it's about your workload, your price performance, and that can be cheaper machines like the A or B series. But even the F series, D series provide a good price performance, middle of the road ratio, particularly if you don't need InfiniBand, you just need some fast cores, some memory, and some disk to be able to get it done. And on the left, you'll see that these things are real. So the cloud is not just some nebulous thing that exists. They're real machines, real data centers. You can go on to the Open Compute project and get specifications of some of these machines. This is actually something that we work on all the time, and you'll see some of the folks there, even in that picture, who have worked on the HC series from Intel in particular. So a little bit more detail on those machines. We have a range of architectures available, and when I said HB, memory bandwidth, and HC for dense compute, we've got the HB machines really relying on the AMD EPYC processors that have really a proven ability to do fast memory bandwidth workloads. So this is when you need, your CPU needs really fast access to the memory. And these come in 60 core on 120 core machines with the AMD EPYC Rome. So the latest machine, the HBB2, is on the very left. And on the right-hand side, you'll also see the HC machine with the Intel Skylake processors. So maybe this type of machine might be better suited to finite element calculations, really dense computing calculations that rely on fast cores to get the work done. All of these are backed by the fastest InfiniBand network publicly available. So this is 200 gigabit second InfiniBand. And that's typically in the HBB2 actually. So the HB and the HC machines rely on 100 gigabit InfiniBand. And then on the right hand side is one of our older HPC machines at this point, but it really has a great capability for core to memory ratio. So it is relying on the Intel Haswell processors, but also can be the right price performance and the right RAM per core that you might need for your job. So we have a number of choices here available. And then in terms of the GPU machines, NV typically refers to visualization. So you have a workstation or an interactive job. And then the NC is really for dense compute, and the ND is for deep learning. So this is a range of machines that you might want to use for some of these workflows. And again, you combine these together for the type of workflow that you need. So spin up an NV machine for your workstation interactive workflow, do some simulations on your NC compute farm for some GPU calculations, and then maybe for some deep learning on large data set, you might prefer some of the ND machines. This gives a little bit maybe of also an overview, and moving from the left to the right hand side, we're also increasing in terms of the performance of the option, possibly as well in terms of the cost of the option. But again, it's about maybe what is the right combination for your job to get done in the quickest amount of time at the right price. So maybe you can rely on Azure Blob Storage, which also has tiers available in terms of hot, cool, and archive. So data you're not using can sit very cheaply in archive data, and you can move that very quickly to a hot tier that you might be able to use for limited types of simulations. Typically in HPC, we are seeing a lot more where we've got disks directly attached to machines. We're doing parallel file systems with machines and disks attached that then get shared to the compute nodes to run the simulations. We also have native solutions as well that have come to us through acquisition over the last number of years, like Azure, the HPC cache product that we have currently. And this also allows you to really have a great hybrid scenario, combine existing on-premise NFS shares directly into Azure. Your compute nodes in Azure and your compute nodes on-premise can see the same data share, the same NFS structure, and beneath the scenes, Azure is, or the HPC cache product, either of them are caching the data as is used intelligently. We also have a native service with NetApp. So Azure NetApp Files is has a lot of scenarios together, and in one of the recent performance benchmarks on the Azure NetApp Files site, you'll find that they used SUSE Linux machines to be able to create clusters to do that level of performance, but it really gives a great combination for read and write performance for a lot of simulations. And then again, at the high end of the scale, we've got Cray Cluster Store available to you in Azure for multi-petabyte large-scale parallel file systems. In terms of moving data in and out, super quick. You can use third-party tools to do that, to manage and accelerate the file transfers in and out of Azure. We have a native tool called AZ Copy that will also do that for you. And then there's offline and online solutions from Azure to be able to do it. So tools that will sit on the edge in your data center and syncing data back and forward to Azure Blob Storage, or also you want to ship this stuff on a disk, on a box, you multi-petabytes that you want to get in quickly. These are also options available to you. So again, a wide range of options that we see in HPC, and it's about finding the right combination for you to get the simulation done. So we're coming to the end of the presentation. I hope it's been useful so far to give you a bit of an idea of the range of options that are available, how much also this capability has grown at Microsoft in the last number of years, and how much it will continue to grow. So please join us, join this community, join testing out how you can use Azure for real HPC and use SUSE to do that. So SUSE Linux, the SUSE Linux HPC pack, and different architectures around that. You'll find solutions online using GitHub as well, where people are sharing solutions that they use to put some of these clusters together. And this is the great capability that we have now in the cloud, to have all of your infrastructure, a complicated infrastructure, combined together in a simple point-and-click interface and a simple repeat that with a single command that you can really redeploy this infrastructure together. So in terms of summarizing, we have a comprehensive portfolio available in Azure. So this doesn't include just IaaS, but also PaaS and other hybrid solutions. We facilitate all the existing tools you know and love. So we also have additional tools to make it easy to transition to the cloud, to use some of the cloud native capabilities we've got, and to lift and shift clusters, for example, that you might already be used to using on-premise. We're talking about integrating this with intelligent solutions, so putting artificial intelligence and machine learning also at the heart of some of these problems that are solving. It's about what is the best way to get the problem solved. So we can really combine this a lot more natively in the cloud together with other data solutions and device solutions, IoT, and that's what is really going to bring HPC also to new scenarios. We have a huge partner ecosystem. Again, very proud to have SUSE a big part of that, and we work with them very closely on many customers. And finally, there's a large investment also by Microsoft in HPC, and hopefully that's also been evident from the presentation you've seen. Colleagues, hopefully, that you'll meet in the field with deep HPC knowledge, deep Linux and HPC knowledge, working at Microsoft to bring HPC basically to everybody. So that's it, everybody. Thanks very much for your time. I hope to see you soon at another SUSE event. Please feel free to contact me if you have any questions regarding SUSE HPC. You'll find me on Twitter, you'll find me on LinkedIn, and please stay safe, take care. Thank you very much.